All right, it is 1 o'clock. How's everybody doing? Ready for the weekend?
Yeah, for sure.
Yeah, I gotcha. I understand. I understand. Is there any questions anybody has about anything? I mean, maybe I shouldn't say about anything, but about almost anything. No questions? Everybody's doing well? All right. Well, I guess we can begin. All right, y'all can see my screen, right?
Yep.
All right, so today, implicit differentiation. So let's kind of talk about what that actually even means. So all the functions that we've really used so far this semester, and probably mostly in your mathematical career, are called explicit functions. So explicit functions mean that I can solve for y in terms of x. So these are two examples of explicit functions, right? But we do have something called implicit functions. So x squared plus y squared equals 25, that's an implicit function. But we could actually solve that for y. So that can go either way. But when we talk about number 2, x cubed plus y cubed equals 6xy, that we can't really solve for y. So what do we do if we need to take the derivative of something like that? So let's continue on. So here's some explicit functions. Here's some explicit functions. Just another slide of them. So do you guys see the difference between implicit and explicit functions? Is there any question about any of these?
All good.
All good. All right, good. So, so we could, like I said, we could solve equation 1, which was here, x squared plus y squared equals 25. We could solve that, and we would get plus or minus the square root of 25 minus x squared. So we have two functions, and we'd actually have to determine, when we're solving this, which function is we're using, because there is a plus and there is a minus function. If we were to graph it, so x squared plus y squared equals 25 is a full circle with a radius of 5, because that's the equation for a circle. But if I have to explicitly solve it, I have these two semicircles, and it depends on which one of these semicircles I need to decide which function I'm going to use, right? Like if I said I want to find the derivative of x squared plus y squared equals 25 when x equals half, well, what does that mean? Like, which function am I going to use? Do you understand why it's not great to do that? So does everybody understand what I'm saying? Okay, I'll assume that's a yes. So if we want to find the derivative of y with respect to x on a function like that, we're going to do it. I'm going to show you how to do it implicitly, because explicitly, I think you've already basically have an understanding. So for example, here I have x squared plus y squared equals 25. And remember, I said that every single function that you take the derivative of always includes chain rule. Although sometimes you don't see where the chain rule is. I'm gonna show you where the chain rule is, and I'm gonna show you why I'm saying that. So if I look at x squared, I'm gonna say my inside function is x and my outer function is squared. Is that okay? Does everybody understand that? And the same thing for y. I'm going to say my inner function is y and my outer function is squared. So what I'm going to do is I'm going to take the derivative of this x squared, which as you know is 2x, but also I'm going to take the derivative of x. So that's the derivative of x, and notice it's with respect to x. I know this looks ridiculous, and some of you are saying, why are you doing this? But there really is a reason for it. Okay, we're going to use it here, and then we're going to use it in when we get to related rates and application problems. So it is really important to understand what this means. And then I would say for the y, I would say this is 2y, but now the inner function is the derivative of y with respect to x. And that's going to equal the derivative of constant, which is 0. So I'm going to stop here for a second and make sure everybody understands what I'm doing.
Why? Can you explain why the 2x is dx over dx?
Sure, because what's the derivative of the inner function is really x. Of this inner, the derivative of the inner function is the derivative of x, but since I'm taking it with respect to x, in the end, this actually cancels because dx over dx just goes to 1.
Okay, okay, okay.
So that's why you never see it, but I wanted to show you that it's there.
Oh, okay. It's like one of
Okay,
the. Okay, I get it. I get it. Thank you.
you get it? Because sometimes we might take the derivative of this with respect to another variable like t, and then you can't forget to take the derivative of that inside function with respect to whatever the variable is we're talking about. So here we're talking about with respect to x. So I just wanted to show you that. Okay, so now I want to solve for dy. Sorry, I want to solve for dy dx. So I end up with 2x plus, actually, I'm going to subtract the 2y dy dx from both sides. So I get 2x equals negative 2y dy dx. I divide both sides by negative 2y, and I end up with dy dx is equal to negative x over y. Okay? So I've taken the derivative. Now, so here we go. We have dy dx equals negative x over y. All right? So if that's okay, I want to erase, whenever you're ready, I want to erase this bottom here because I want to do B.
I'm good copying personally.
Yeah, when you're done, just let me know.
I'm good.
Okay, is everybody done copying? All right. All right, so now find an equation of the tangent to the circle, x squared plus y squared equals 25, at the point 3 comma 4. What do I do?
You plug in the 3 comma 4 into the negative x over y.
I do, right? And that gives me what?
Negative 3 over 4.
No. What, I'm sorry, that was a bad question. You're right, it does give me that.
My bad.
So
Plug it
what
into
is,
the actual equation x squared plus y squared. Oh,
um,
I was right. Never mind. No, 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 no. I was thinking to plug it into the negative x over y, which is what you did.
yeah, which is what we did. Exactly. You just plug in the point and we get dy dx. But what does dy dx mean? If I want to find an equation of the tangent line to the circle, what does that mean?
That's the slope.
Good. So that equals the slope. So if I want to find an equation of the tangent, we're talking about a line. So I can say, I can use y minus y1 equals m times x minus x1. And there's the answer. Is there any questions about this?
No, I'm good.
All good? Everybody's good? All right. So now this problem, we can't really solve it for y, can we? Like we can't make it explicit. So what can we do here? Does anybody want to give it a shot? Not Soraya? Nick, come on, you're brave.
I am. I'm looking at it. Would we solve it for sine of y?
No, we're not solving it. We can't really solve for y. So we're
Okay.
gonna see. Do you see that we can't solve this for y?
Yeah.
Because we would have y in terms of y, wouldn't we?
Mhm.
So what we have to do is implicit differentiation, which is what we're learning today. So how would I solve? What can I do with 2y? If I want to take the derivative of 2y, what do I get?
We'll just get 2.
I get 2. But what about this y? What happens when I take the derivative of y? Because remember, I want to do dy dx.
Yeah. So you'll have the derivative of y with respect to y there. That's
Not
the
with respect to y. We have the derivative of y with respect to x. We're going to differentiate this entire thing with respect to x.
Okay.
Because what I want to find is this. And remember, we're trying to find the slope, aren't we? And the slope is going to be, if I were to graph this, the y would be the vertical axis and the x would be the horizontal axis, so dy dx is the change in y over the change in x, which is the slope, right?
Mm-hmm.
That makes sense?
Yeah.
So do you understand why I have 2 dy dx?
Yeah.
Okay, good. So that's going to equal what?
You'll have 2x,
Right?
and then
Plus,
derivative.
uh-huh.
Would you do? Wait, so you don't do derivative x yet, like derivative x with respect to x?
You can, but that was just there like for show. So derivative of x with respect to x is always 1. That's why you don't have it in there. That's why the derivative of x, as long
Mm-hmm.
as it's with respect to x, is always 1.
Mm-hmm.
Right?
Yeah.
Does that make sense? Like if I say take the derivative of y equal x, we have dy dx is equal to 1. But
Mm-hmm.
in reality, it's equal to dx dx. But we
Okay.
don't need dx dx. We just need 1.
Okay, that makes sense.
Okay, good.
So it'd be
Perfect.
plus cosine y.
Plus what?
Cosine y.
Cosine y. Yes. But remember, we have a chain rule, and my inner function is y now.
Mm-hmm.
So now I have to say, oh, that's dy dx, the derivative of y with respect to x.
Okay.
Okay, make sense?
Yeah.
All right, good. Now I want to solve for dy dx. So what do I have to do?
Divide everything by 2.
Is that how you solve things? You divide first?
Mm.
I don't think you do. Think about what you do. So if I said y equals, or 2 minus y equals 3 plus x, do you or 2y, do you divide everything by 2 first?
No.
No. So think about what you really do. Think about dy dx as a variable that you're trying to solve for. So
So
what do you
you
do when you
want
try
to
to solve for a variable? I'm sorry, Nick, go ahead.
subtract the cosine y times dy dx over to the left side of the equal
Okay,
sign.
cool. I can do that. So I have 2 dy dx minus cosine of y dy dx is equal to 2x. Good. Now what?
You could take out a dy dx.
Yes.
So you would have dy dx and then parentheses 2 minus cosine.
Good. And then,
Hold on, I'm copying. And then would you just divide that whole
yep,
parentheses from dy dx?
yep, exactly. And there's my derivative of y with respect to x is equal to 2x over 2 minus cosine of y. Exactly. You just want to think of dy dx as a variable. Now we can also do this with y prime, which sometimes is really helpful because it's just a lot less notation. So we'll do the next one with just y prime. Sometimes it's not good, sometimes it is good. You'll have to see when what the differences are, okay? So is everybody good with this? Any questions here?
I'm good.
All right. So now we want to find the equations of the lines tangent and normal. Does anybody remember what we talked about as far as what a normal line is?
Isn't the normal perpendicular to the tangent?
Exactly. So if once I get the tangent line, what do I need to do to find the normal line?
It's the negative reciprocal of the slope.
Exactly. Everything else is exactly the same. Perfect. Very good. Who was that? Was that Enroy?
Ramari.
Oh, Ramari. Sorry, Ramari. I guess I can't do just voices yet. Okay, Ramari. You want to give this a shot with me?
I guess I will.
Okay, if you do it, you do it. If you don't, you don't. This one we're going to do with y prime, so I'll show you what I mean. So let's start. What's the derivative of 2x? I'm sorry, what's the derivative of x?
2x.
2x, yeah, sorry about that. Now, here's an interesting thing. We have minus
xy.
xy. What do you think we have to do for that?
What do you say, the product rule, or?
We do. We have to do the product rule, don't we?
I guess.
Okay, so I'm not sure. Let's see if we can do it without doing a lot of work on the side.
Mm-hmm.
We just have to remember that if y equals fg, then y prime is equal to f prime g plus g prime f. So let's just write that formula down. And then, so let's just see if we can do it. So f is going to be x and g is going to be y, okay?
Yeah, so that would be, is it minus y?
Well, I'm going to say minus, I'm going to put the rest of it in parentheses.
Okay.
So I have y, exactly.
Wait, do you have to put, I get you. All right, so
Okay.
it's y, plus, minus x. Is that minus x?
Well, we're only really taking the derivative of xy because I have the negative on the outside of the print.
Oh, okay. So just be x, right?
Well, kind of, but remember, so g prime, if g is y, then so I have to say y prime here, don't I?
Yeah.
Times x, because f is x. Here,
F
so I
is
said
x.
f equals x and g equals y. So f prime equals 1.
1
G prime equals
equals
y.
1.
No, it doesn't equal 1.
Isn't it 1?
1 if we were to take the derivative with respect to y.
Oh, okay. I get you.
Get it? Is everybody starting to get this? I just want to make sure we're going to do this over and over again until like it all starts to click together. Is that everybody with me? I know Ramari, I know you got it, so thank you.
Can you re-explain that again? Can you re-explain that again? Can you re-explain why it's not 1 and why it's y prime again?
Sure. So let's just write it instead of with primes. If I want to know what dg dx is, isn't it dy dx? Here, if I want to know what df dx is, it's equal to dx dx, which is 1. But dy dx is not 1 because dy over x is not always 1, but dx over dx is always 1.
Gotcha.
Yes, really?
Yeah, I do.
Okay, good. So you don't have to use the y prime. I'm just showing you how you can do it with a prime instead of with the Leibniz notation, the dy dx. Is everybody okay still? Okay, Ramari, let's do the next one. Y squared.
Okay. So that's 2y dy dx.
Yes, I'm just going to use y prime just because I'm doing it a different way this time.
Oh, yeah.
You could use dy dx there instead. They're the same. Okay? Good. And that equals what?
0.
Good. Now what are we going to do? Well, let's distribute the negative. Let's just take those parentheses. So we get minus y prime n plus 2y y prime equals 0. Okay, good.
What are you going to do? What are we
trying to solve for?
See, is it x?
No, we took the derivative because we're trying to solve for
For y?
y prime, right? The
Yeah, y
derivative of
prime.
this function is y prime dy dx. That's what we're
Oh
looking
yeah.
at.
So we'll put the 2x minus y over to the right. So
Okay,
that'll be minus. So it'll be minus y prime x plus 2y and y prime
good.
equals minus 2x plus y.
Perfect. Beautiful. Now what?
And then we'd factor out the y prime.
Exactly. I'm just gonna switch these. Just I like positive things leading,
Okay,
but
okay.
either way is fine. It's just my preference, honestly. It doesn't mean anything. Okay, good.
And then we divide the right side by both sides by 2y minus x.
Yep, exactly.
And then we got y prime.
Now we have the derivative. We did it implicitly, right?
Mm-hmm.
Okay, now what are we gonna do next?
And if that's the slope of the tangent, then we'll take the negative reciprocal of that to get the
Well, first
normal.
let's do this. Let's plug in our numbers.
Oh yeah, that would be
That's
easier.
not a very good, that's a pretty rough slope.
Yeah, that's true. That's true.
Okay, so what does it equal?
It would be 2 plus 2, 2 plus 2
Mm-hmm.
over 4 minus, well, it'd be plus 1, right?
Exactly. So we have 4/5, right?
Mm-hmm.
Okay, good. So let me just change colors here to make it a little. Okay. So here in this little box, okay, we have the tangent line. What's the tangent line
The
equal to?
tangent line is y minus 2
Uh-huh.
equals 4 over 5
Yes.
x plus 1.
Perfect. And then what is the normal line?
For the normal line, it would be y minus 2 and then negative 5 over 4
Yep.
x plus 1.
Perfect. There you go. Great job, Ramari. Excellent.
I tried.
Excellent. That was great. That was great. Is everybody starting to get this now? Is it
I have
starting?
I have one question.
Yep.
At the first red line on the top underneath the original question, it says 2y y prime. Can you explain just why it's 2y y prime and not just
Yeah,
2y?
because remember, think about the inner function as y.
Yeah.
So I'm taking the derivative, I'm using the power rule, so it's 2 times y to the 1 power, which is 2y, right?
Yeah.
Times the derivative of the inside function. And the inside function is y, so it's the derivative is y prime or dy dx, whatever you like. You're welcome to put dy dx instead of y prime. I just think most people really prefer the primes because it's just a little less writing. But I'm perfectly, I probably most of the time I use dy dx myself. It just makes me feel more comfortable because it keeps me remembering what I'm taking the derivative with respect to.
Okay.
Did I answer your question, Nick?
Yeah.
I did? Okay, good. Any other questions? All right. Let's see, should we do another one? But we did one kind of like this. How about if we do this one now? This one's a little more complicated. Anybody want to give this a shot? It's a little more complicated. Just a little. Nobody? I'll call on somebody. I only know so many people's names who are here, so I'll call on somebody though. All right. Don't make me call on you. You can just volunteer. Okay. So what are we gonna do? It is a little more complicated. I'll make sure you get it. Don't worry.
So first we can do the derivative of sine xy.
Yeah.
So can we take the it would be sine of u. Can we do substitution for this one or no?
Absolutely, absolutely. So we want to say u equals x times y.
Yeah, and then y would be sine of u.
Then y is equal to, here, let me So here's what I want to say. Yes, you're right. There's nothing wrong with what you said, but you might want to actually, here, I'm going to write y equals sine of u way down here, and I'll show you why. So how are we going to take the derivative of u?
Well, first we got to do the product rule.
Right, exactly. So I'm going to use du dx. I'm going to use dx's now. I'm
Yeah.
going to get away from the primes right here.
So then this one would be, it would be y plus x times dy dx.
Okay, exactly.
And then that's the derivative. And then now we have to do the derivative of.
So we want dy.
Yeah, that one's.
Uh-huh.
Which is cosine of u.
Perfect. Good. So now we can put this together.
Yes. So now we get cosine times y plus x times dy over dx.
Cosine of, so u is equal to xy.
Oh, my bad. Yeah, xy, my bad.
Okay.
And then now times y plus x times dy dx.
Good. Very good. So
And
this
then,
is equal to what?
And then now it will be equal to
dy. This is equal to dy dx, right?
Yes.
Because we took, so let's see, dy du dx. Yeah, that's equal to dy dx. Okay, good.
Yeah.
So we have that side. So I know now, here, I'm going to just put a little line here. So the derivative of this sine of xy is equal to the cosine of xy times y plus x dy dx. And that equals, go ahead.
It equals to 1 plus dy over dx.
1 plus dy dx. Good. Very good. I think you guys are getting this. Okay. Now what?
All right. So we have dy over dx on that side. So can we subtract that dy dx to the other side?
Which one? The one on the left?
On the right side. On the right side.
Sure. So I have cosine of xy times y plus x dy dx minus dy dx equals 1. That's what you meant, right?
Yes, correct.
Okay.
And then now we could not factor, but bring the dy dx on the outside.
How would I do that?
You would have negative dy dx times x. Hold on.
Be careful. You have to distribute first.
The cosine, yeah. All right, so it'll be cosine
I'm
xy.
going to put that y on the front here like this. It's just a little easier to look at if we do it like this. It's not wrong to put it at the end, but it'll be confusing if I put it after that parenthesis. Does that mean I'm going to multiply that by xy, or do you understand?
Yes.
So it's better. I think it's better to put it in the front. But okay, yes. Plus.
All right. Plus cosine xy.
I'm going to put the x up front again.
Yeah. And then dy dx, and then we have minus dy dx.
Okay, good. I like it.
And then now we could do can we subtract the y cosine?
Yes.
All right.
So I'm going to just write this left side here first. All right, I think I got that right.
All right, and then now we can not distribute, but break it. We could break it apart the left side, so dy over dx on the outside. And then times.
The word you're looking for is factor, by the way. But yes.
Factor, yeah. Okay.
Yeah, you were right.
Professor.
I knew it.
All right. So now we do x cosine xy, and then minus 1. And then now we can divide both sides by x cosine.
So we have 1 minus cosine of xy over x cosine of xy minus 1. And that's
Yes.
good job. Excellent. Thanks.
Thank you, Professor.
No, thank you. That was a great job. Great job. Is everybody starting to get the hang of this?
Slowly, yeah.
Okay. I know. We'll do it. We'll just keep doing examples. I can go back to what we didn't do. Like, I want you to feel comfortable before we do the breakout rooms, as long as I have time to make you feel comfortable, which so far we're doing well with timing. So don't worry. And then the rest of it you'll get in the breakout rooms. Okay. Do you want to go back and do the one that we didn't do? I think this one we didn't do. Or do you want me to skip off it? Because I don't have too many more examples. Should we do this one?
Let's do this one then.
Okay. Does anybody else want to? So I just want to let you know, and I think that the people who participate can agree with me that the more you participate, like when you're done participating, you understand it better than just watching somebody else do it. Do y'all agree?
Yeah.
The people who tried, yeah. So just give it a shot. I'm not going to let you fall, I promise. I'm going to catch you. Anybody want to volunteer? All right, I'm going to pick somebody. How about Michael? It's Michael. I know Michael's here.
Yeah.
You want to give it a shot?
Sure.
You go by Michael or Mike? I don't think I've ever called your name.
Either one works.
Which one do you like best?
Just go Mike.
Okay, Mike, let's do it. All right, let's give it a shot here. So what are we going to do first?
Well, we have to find the derivative of everything, right?
We have to find the derivative of everything, exactly, yes. So let's start with 3xy. I mean, we could start with 4y squared if you feel more comfortable. I don't really care.
Okay, yeah, that would be 8y dy dx.
8y dy dx, excellent. Very good. And what's the derivative of 10?
0.
Good, we got the easy ones. Let's do the harder one. So one thing we can do first is we can just always pull out
Right.
the constant. So all we really have to worry about is 3 times the derivative of xy, right?
Yeah.
Okay. And so how do we do the derivative of xy?
You would use the product rule.
Exactly. You want me to write the product rule down for you?
F prime g plus g prime f.
You got it. So what do you want to call f?
X
And then g?
would be y.
And then f prime?
Would be 1.
And g prime?
Would be dy dx.
Good. Perfect. Okay, let's do it.
So it would be y plus dy dx.
Almost.
Y plus x dy.
Yes. Perfect. Perfect. Okay, now what? We want to find dy dx, right?
So you would multiply the 3 times. Yeah.
Yeah, I got you. I understand. All right.
And then you want all the ones with dy dx on the same side. So you would multiply, or you would subtract 3y.
Good. Mm-hmm.
Then you factor out the dy dx.
Good. Good. Last.
Then divide the 3x plus 8y to the right side.
Perfect. All right. Well, I think everyone's starting to get it. I mean, I don't know if I'm just lucky calling on people who are getting it or not, but good job, Mike.
Thank you.
Thank you. Any questions about this? Okay. So we got that. So now we can take higher order derivatives, okay? I actually have this one going, so I'm just gonna let the screen do it. Or we can do it ourselves. Which would you rather? Would you rather let the PowerPoint do it, or would you rather us do it ourselves? I don't really care. It's probably ourselves? Okay,
Yes.
we'll do it ourselves. Let's do it. So the first thing if we want to find the second derivative of this function, what do we have to do first?
Hold on, I'm erasing stuff.
What?
Hold on, I'm erasing stuff.
Okay. Now, when we want to do higher order derivatives, I just want to say I think it's easier to use primes. So we want to really find y double prime. If you feel like it's easier to do it the other way, that's perfectly okay with me. But I think it might be easier because it gets to be a lot of letters on the screen. So we'll just try it this way and see if it's okay. Okay. Do you want me to do it, or does anybody want to do it with me? Nobody? Okay, I'll just do it myself. So first I'm going to take the derivative of 2x cubed, which is going to be 6x squared, right? Then I'm going to take the derivative of the next one, which is minus 6y. And I have to take the derivative of y. So we get, I'll just do y prime. I think it is easier with the primes in this one. And that's going to equal 0. Okay? And now I'm going to solve for y prime. So I'm going to subtract, I'll just subtract the 6x, so this equals minus 6x squared. Divide both sides by minus 6y. So I get y prime is equal to x squared over y. So did everybody follow that? I know I do it a lot more. I do it more quickly when it's just me, I know. So did everybody get that, or did I go too quickly?
I got it.
Okay. So I'm gonna. Now we need to take second derivative. We take the derivative of this again, but the derivative of y prime is y double prime, right? The derivative of the derivative of the derivative is the second derivative. Is everybody okay with that?
Yep.
Okay. And now I have a quotient rule. So I guess I should probably do the work here. So if I say f is equal to x squared, then f prime is equal to 2x. And if I say g is equal to y, then g prime is equal to y prime, right? And what kind of rule am I going to do for this one? I have to do the quotient rule, which is f prime g minus g prime f over g squared, right? So the derivative of f is 2x times g, which is y, minus g prime, which is y prime, f, which is x squared, over g squared, which is y squared. Agreed?
Yeah.
Okay, good. But I don't want a second derivative in terms of a first derivative, but I do know what the first derivative equals. So I can plug that in, which gives me y double prime is equal to 2xy minus x squared over y times x squared over y squared, which is equal to 2xy minus x to the fourth over, is that right? Oh yeah, over y squared. I'm going to have to get a common denominator. This is not an acceptable fraction. We want a fraction, not a fraction over a fraction. So I'm going to multiply by y over y for the 2xy, which gives me 2xy squared minus x to the fourth over y squared over y, over y over y. Still good? And then that, I'm just going to simplify that to 2xy squared minus x to the fourth over y cubed. And I don't think I made any mistakes. I'm not sure. I think it's all good. Did I make any mistakes? Anybody see any mistakes? Okay. So did that make sense now? We're just
Yeah.
taking another derivative, but we want to plug in our first derivative into our second derivative.
Professor,
Yes.
I feel like you keep telling me the same reason why. I just need to try and get into my head.
Okay.
But when we had to use the quotient rule, we were labeling f prime, g prime. Why is g prime not 1?
Because we're taking the derivative with respect to x.
Mm-hmm.
If we wanted to know what the derivative of x with respect to y is, now let's just say I wanted to find that. Do you want me to do that problem? Maybe that'll help.
Yes.
Okay, let's do it. Here's what I want to do. I would have to erase everything. So I need to make sure everybody's got everything copied before I erase.
I'm good.
Okay, is there anybody who's still copying? Okay, maybe this will help. Let's see. So now we want to take the derivative of x with respect to y. Second derivative, okay? Is that good?
Yeah.
Okay, good. So now when I take the derivative of 2x to the third power, I get 6x squared, but now I get dx dy. Because I'm now taking the derivative with respect to y. So I can't say x is 1, because that was when it was dx dx. But now I have 6y, and I'm taking the derivative of y with respect to y, which is equal to 1.
Gotcha.
Did that help?
Yes, it does.
Okay, good. We are going to be starting to take the derivative of things with respect to time when we get to a related rates problem. So you do have to understand what I mean when I say with respect to something. What we're doing is taking the derivative of the dependent variable with respect to the independent variable. Okay? Do you want me to continue, or is that enough? Or do you want me, I don't care, I'll finish the whole problem again if you want me to.
Can we just get to the point where you have to use the quotient rule again?
Yeah, of course. Absolutely. Absolutely. So let's see. I want to take, now I'm going to take this, well, let's solve for dx dy. So I'm going to add 6y to both sides and divide by 6x squared, right? So I have dx dy is equal to 6y over 6x squared, which is equal to y over x squared. Okay?
Mm-hmm.
All right. So now, let me get another color. Now I'm gonna leave it in this dy dx dy format. I think maybe that'll be helpful. I'm not sure. Okay, so now I'm gonna say f is equal to y and g is equal to x squared. So f prime, well, that's just equal to 1 because it's dy dy.
Mm-hmm.
And g prime is equal to
It'd be x
2x
prime.
dx dy. I'm sorry, Nick, did you say something?
So why wouldn't it be x prime there
Where?
for g prime?
It is dy. I have dx dy.
Okay.
See it?
Yeah.
Okay, good. So now let's take the second derivative, which is going to be the quotient rule. So I have the second derivative of x with respect to y is equal to f prime, so here I'll write it down, f prime g minus g prime f over g squared. Okay, so let's fill in the blanks. F prime is 1, that's fine, I don't do anything. G is x squared minus g prime, which is 2x dx dy, times f, which is y. I'll just put the y over here, over y squared, which is, I'm sorry, g squared, which is x to the fourth, right?
Mhm.
You with me, Nick?
Yeah, I am.
Okay, good. But remember, I have to substitute in here the dx dy. So this is going to equal x squared minus 2xy times y over x squared over x to the fourth. And then I can simplify the fraction. If you want me, I'll simplify the fraction again, but literally I'm just going to do that next. Do you want me to
You're good.
simplify it?
No, it's fine. I
Okay.
understand. Thank you.
Did that help?
Yeah, it did.
So it has to do with what you're taking the derivative with respect to. That's the important part, to know whether it's one or you have to put that dy dx or dx dy in there. Or dx dt or dy dt or du dt, or I mean, you can, whatever it is, you just have to know the top is the dependent variable and the bottom is the independent variable. Okay?
Yeah.
All right. So let's see. I think the only thing, oh yeah, I remember I put this all. Okay. So remember I said I couldn't really show you why the derivative of the inverse function is the way it is, because we hadn't done implicit. So if you want, I have two options. Either I can show you why, or we can end here because this is the last thing. It's a little complicated, but it might be interesting. I won't expect you to do it. So if you're interested, I'll do it. If you're not interested, we'll skip it. Is anybody interested?
Here, let's do it.
Let's do it? Okay. So we're starting off saying we want to find the derivative of, so we're saying y equals the inverse. I'm just going to let the PowerPoint show you because I think it'll be easier. And we'll stop at each point, make sure you understand. So then we're going to solve for x here. Okay. So now I have the sine of y is equal to x. And then I'm going to take the derivative. And here I have the derivative of the sine of y, but that's going to equal cosine of y, but times the derivative of y, which is dy dx. And here the derivative of x with respect to x is 1. Does that make sense? Is that step good?
Yeah.
Okay, good. So now we're going to have to solve for dy dx is 1 over cosine of y, right? We just divide both sides by cosine. So now we also know this is the Pythagorean identity, right? That y sine squared of y plus cosine squared of y equals 1. Agreed?
Yeah.
Okay. So now we can say, and remember that I just want to say the last thing we have is dy dx equals 1 over cosine of y. So now we have to find out what cosine of y is. So we're going to solve for cosine of y. And we're going to take the square root of both sides. But when we take the square root, it's plus or minus, right? All good?
Mm-hmm.
Okay, now, so remember that the inverse function is so we're talking about for cosine of y is always going to be positive. Okay, so remember we started off here. What are the bounds on the inverse sine? Does anybody remember? I know I taught you this, so. Does anybody remember the bounds on the inverse? Somebody please from my class remember. One person, please.
Is that
Oh, cosine?
over 2?
Cosine.
Oh,
Because that's
so
what
negative
we're
negative
working
pi
with.
over 2
Negative pi over 2. Good, thank
to
you.
pi over 2.
Good. Does everybody remember that's the bounds for the inverse, right? So we're going to use that and say, well, because it's between negative pi over 2 and pi over 2, which on our unit circle is the right side, that means all my cosine values are positive. So I don't need the plus or minus. It's all positive. Okay? Does that make sense?
Yeah.
Okay, good. So now we have the cosine of y is equal the square root of 1 minus sine squared. And we know that dy dx was equal to 1 over cosine of y from the previous slide, right? We have dy dx equals 1 over cosine of y. That was the end of the previous slide. So we're just replacing the square root of 1 minus sine squared for cosine of y. Okay? So far, so good? Is anybody lost yet? And then I'll show you one more thing. We know that x is equal to the sine of y, right? That's what we said. So when we get down here and we have the sine of y, we can say that is equal to 1 over the square root of 1 minus x squared, which is the derivative of the inverse. And that's that. So I won't make you do this. But I thought it would be interesting to see how these derivatives actually come to be. I don't know if that was interesting. It's interesting to me. If it's not interesting to you, I'm sorry. Is there any questions about that? All right, that's the end. So let me stop the recording. Hold on. I can't find my Zoom meeting. Oh, because I didn't stop sharing. Okay, sorry.